NASA had just committed to a mission unlike anything attempted before, launching a probe toward an object so vast it dwarfed previous interstellar visitors by an almost unimaginable margin. This target was estimated to be nearly 100 times larger than Atlas, an interstellar giant already known for its scale and speed. What initially appeared to be a straightforward scientific interception rapidly evolved into a discovery that left researchers stunned. This was not a passive chunk of cosmic debris. It showed signs of motion beyond gravity alone, reacted to its environment, and left behind evidence that defied conventional explanations. The moment NASA chose to intervene directly, everything changed. This single decision marked one of the boldest steps in the agency's history. For those drawn to stories of exploration and discovery, this was the kind of moment that reshaped humanity's understanding of the universe. As with many groundbreaking discoveries, the event began quietly. There was no dramatic explosion or immediate announcement, only a faint point of light drifting slightly faster than expected across 3 consecutive frames of sky survey data. At first glance, it seemed like a minor anomaly, a flicker easily overlooked. But automated detection systems noticed something off. The motion did not match known objects. That flicker quickly became a red flag. Astronomers reviewing incoming data from the Pan-STARRS survey and the Vera-C Rubin Observatory flagged the anomaly and forwarded it to NASA's Minor Planet Center for further analysis. Within just 36 hours, the object received a preliminary designation, X100. Almost immediately, it also became a serious concern. Calculations showed it was entering the solar system at a speed far exceeding anything listed in existing asteroid catalogs. Its path was unmistakably hyperbolic, meaning it was not bound to the Sun and would pass through once before escaping back into interstellar space. This trajectory placed it in the same rare category as earlier visitors like Oumuamua and Atlas. But there was a critical difference. X100 was not small. It was enormous. Based on reflected light measurements and Doppler shift analysis, scientists estimated X100 to be at least 100 times larger than Atlas. Some models suggested a radius exceeding 2 kilometers. That alone pushed it beyond the range of comfortable observation. Objects of this size, arriving this fast from beyond the solar system, had never been encountered before. Dr. Anna Avuz, head of NASA's Planetary Defense Coordination Office, summarized the gravity of the situation plainly. This was not merely a rare opportunity for study. It was a stress test for humanity's readiness. Time became the most unforgiving factor. Updated orbital solutions revealed a rapidly shrinking window. From the moment X100 was confirmed, NASA had only 58 days to attempt any kind of interception. Simply watching it pass through telescopes would not be enough. Once it left the inner solar system, whatever information it carried would be lost forever. That reality forced a difficult but historic choice. For the first time, humanity would attempt to intercept a massive interstellar object before it slipped beyond reach. The mission's objective went far beyond distant observation. The plan was to approach within 1,000 kilometers and return high-resolution data no ground-based telescope could ever achieve. The probe would need to be fast, lightweight, and capable of autonomous decision-making. It was designed to pursue a target that would not slow down or wait. As one mission planner put it, sometimes the universe does not offer second chances. Size alone, however, was not the only reason for urgency. X100's behavior raised deeper concerns. The way it moved, combined with hints about its internal composition, suggested it might pose risks beyond academic curiosity. Understanding it became a matter of preparation, not just discovery. Initially, researchers assumed X100 was a massive comet originating from another star system. That assumption quickly unraveled. Measurements indicated an unusually high mass and a density more consistent with solid metal or stone than loosely bound ice. It did not resemble the fragile rubble piles typical of comets. And yet, it exhibited activity. Spectroscopic analysis detected jets of gas venting from its surface as it approached the Sun. These emissions were likely carbon monoxide and cyanide compounds, escaping through fissures warmed by solar radiation. Cleve. Mission analyst Shirao Jean issued a stark warning. This mission was not only about learning something new, it was about readiness. If an object like X-100 were ever captured by gravity during a future pass, humanity would need to understand exactly what it was dealing with. This trajectory only deepened the mystery. X-100 entered on a perfectly retrograde path, cutting against the plane of the ecliptic. Such an approach was not just rare. Statistically, it bordered on unnatural. Some scientists theorized it might be debris from a failed star system, or even the remains of an ancient planet ejected by a supernova. Others focused on its subtle but measurable acceleration, a non-gravitational drift similar to the anomaly that made Oumuamua famous. The question lingered uncomfortably. Was X-100 entirely natural? Possibly. Was it simple? Absolutely not. As one analyst carefully stated, while there was no evidence it was artificial, there was also no proof that it was not. With that uncertainty, the next step became unavoidable. If X-100 carried answers, the only way to obtain them was to intercept it directly. That presented enormous challenges. Unlike missions to moons or asteroids, there would be no orbit insertion, no prolonged study. X-100 was racing through the solar system at more than 80 kilometers per second on a one-way escape trajectory. There would be only a single opportunity. NASA evaluated several platforms capable of rapid adaptation. After intense debate, officials approved a modified Draco-class interceptor. Originally designed for planetary defense experiments, it would be repurposed for this unprecedented chase. The launch vehicle would be a Falcon Heavy, stripped of unnecessary mass to maximize speed. The payload included a compact spectrometer, high-resolution imaging systems, and a radiation-hardened data core. There would be no sample return. The mission was a flyby, designed to collect as much information as possible in a fleeting encounter. The timeline was brutal. The probe had to leave Earth orbit within 29 days, bypassing traditional planning and testing cycles. Engineers worked around the clock to reprogram autonomous navigation systems capable of handling extreme velocities and complex gravitational dynamics. The flight plan required a lunar flyby for gravity assist, followed by a hyperbolic burn to match X-100's trajectory. Every fraction of delta V mattered. Too slow and the probe would fall behind. Too fast and it would overshoot the target entirely. The margin for error was razor-thin. A deviation of just 0.1% in velocity could result in missing the intercept by tens of thousands of kilometers. Lead navigator Emma Kulik described it as threading a cosmic needle at 80,000 kilometers per hour. This was not a conventional mission. It was a slingshot with a single shot. Communication limitations added another layer of risk. Signals relayed through the deep space network would experience multi-minute delays. As a result, the probe had to operate independently. 48 hours before closest approach, it would switch to full autonomous intercept mode. After that, no course corrections from Earth would be possible. Heat shielding was reinforced, not for atmospheric entry, but to survive intense solar radiation. The trajectory would bring the craft within 0.42 astronomical units of the Sun, pushing its cooling systems to their limits. There was no backup mission. As mission director K.G. Thorne stated bluntly, the stars do not wait, and neither does X-100. The launch window opened on a narrow December morning. Conditions were ideal. Weather systems cooperated, and all ground systems reported green status. At 6:44 Universal Time Coordinated, the Falcon Heavy roared to life, tracing a bright white arc through the sky. Less than 9 minutes later, the payload settled into low Earth orbit. After 3 precisely timed burns, the probe departed Earth's gravitational influence entirely, accelerating to speeds capable of escaping even Jupiter's pull. Mid-course corrections began almost immediately. Onboard star trackers and optical sensors searched for X-100's faint glow among the background stars. For the first few days, telemetry from Earth helped refine its path. But once the probe passed the halfway point, communication delays became too severe. From that moment on, the craft was on its own. Every 90 seconds, the probe recalculated its trajectory, accounting for solar radiation pressure, subtle gravitational influences, and the increasing distortion of spacetime as it approached perihelion. One incident nearly ended the mission. On the 12th day, a solar flare caused a temporary sensor blackout. For nearly 17 minutes, the probe lost track of X-100 entirely. When it reacquired the target, predictions showed a drift of 46 kilometers. Engineers rushed to upload revised logic, but ultimately the onboard system stabilized the course. As final approach neared, the probe entered intercept mode. Radiation shielding deployed. Instruments rotated into forward alignment. High-speed cameras began capturing test images. At first, stars appeared as blurred streaks. Then a growing gray mass emerged. X-100 was finally in view. A final adjustment corrected for angular deviation caused by dust scattering ahead of the object. Now, everything depended on milliseconds. A miss would be permanent. One engineer compared it to throwing a needle across the Grand Canyon and having it pass through another needle in midair. During the final 72 hours, there was nothing to do but monitor and wait. Humanity was about to encounter an interstellar visitor directly for the first time. What the probe saw defied expectations. X-100 did not resemble any comet or asteroid previously catalogued. As the craft closed in, cameras captured an irregular, sharply contoured silhouette. The object was not rounded but jagged, almost geometric in form. Its surface reflected light unevenly, flashing between bright, polished regions and deep, light-absorbing voids. Spectral instruments scanned for familiar substances such as water ice, carbon dioxide, methane, and other common volatiles. The data that returned made little sense. Absorption lines did not match known patterns. Instead, they suggested the presence of complex organic materials or unfamiliar silicate structures. One spectrogram even indicated trace amounts of technetium, an unstable element that should not exist naturally without ongoing nuclear processes. In that moment, as data streamed back across the vast distance, it became clear that X-100 was more than a scientific curiosity. It was a message from beyond the solar system, carrying questions humanity had never before been forced to confront.